Hello everyone, welcome back to another video. Today we're going to be looking at the May-June question paper 2, the year 2024. This is grade 12. Okay, we are looking at question number 9, which also focuses on circle geometry. Okay, now the statement reads as follows. In the diagram, AB is a diameter of the circle with the center F. We have a diameter AB, that is the diameter, and we're told that F is the center of the circle. Okay. Now, AB and CD intersect at G. We have AB and CD intersect at this point G. Okay. FD and FC are drawn. This FD and FC are being drawn. And then BA bisects angle CAD. So BA bisects angle CAD. BA bisects angle CAD. Okay, and D1 is equal to 37. That's D1. Okay, two things to note here. First thing is that we are told that AB intersect at DC. Okay, it's very important to note the wording here that they are saying intersect and not bisect. Okay, so if AB intersects at this point, it means that it does touch this point, but they don't necessarily say that it does what we normally know, that a line drawn from center to a specific, like a line drawn from center intersecting a chord will bisect that chord. At the moment, that is not the case. They are not mentioning anything like that. The second one is that they are saying that the line BA bisects angle CAD. And what does it mean when we say something bisects an angle? So if we have an angle here, try to draw it. If we have an angle, let's say is 40 degrees, right? The angle is 40 degrees. Let's say that angle is this is B, this is B, this is A, and this is C. So ABC, angle ABC is equal to 40 degrees. If we draw a line like this, that cuts this angle into 15 degrees and 25 degrees on the side. There's a line that cuts angle ABC into 15 degrees and 25 degrees. That line doesn't cut that angle into half. And what we just say that line just cuts that angle. But there's a special line now that will cut this guy into half. So there's a line that goes like this and cuts 40 degrees into 20 degrees and 20 degrees. We call that line a line that bisects that angle. It cuts that angle into half. All right, let's go with the question. When we say BA bisects angle CAD, it mainly means that A1 is equal to A2. All right. Now let's go to the first question. First question is saying determine and giving reasons any three other angles that are equal to angle D1. Any three other angles that are equal to the angle D1. Okay. Now where is D1? D1 is at that position, okay? But on the circle as a whole, D1 is situated on the circumference, okay? But also angle D1 is surrounded by two chords, chord DB and chord CD. So those are the two chords that make that acute angle. This is the chord, this is another chord. They make this angle. All right. We can also say that this angle is in this triangle, DBG. Here's the angle. So there's three special things about it. It is situated at the circumference. If you look at it, it doesn't fly and not touch the circumference. It's actually sitting at the circumference at point D. But it is made by DB and CD. Okay? It is also in this triangle. Now they're asking us to find which other angles are equal to this angle. Okay. Now, one thing I have seen here just by analyzing where this angle is situated is that when I mentioned DB, DB comes from the circumference. Okay, DB comes from the circumference. So B to D is at the circumference, and C to D is also C comes from the circumference. That's why I said those are chords. Okay, what is special about this is that this angle, if you were to just remove this, just remove it for 1 second. Okay, this angle is subtended by this arc. That angle is enclosed by the arc BC. Okay, now let's bring back the line that we just removed there. This is for you to just add another feature on that angle. So we know that that angle is at the circumference. That angle is in a triangle BDG. That angle is enclosed or is made by DB and CD. But there's something special now is that that angle is also enclosed by the arc BC. Okay. But notice that this very same arc that encloses this angle also encloses this angle here. Look at this. It encloses angle A2. Okay. A2, so effectively looking at something like this here. Okay, we have A2, we have angle D1, we have B, and we have C. So these two angles here are equal. Those are angles subtended by the same arc. That's the theorem. Or angles in the same segment. What other thing? If we had a chord BC, they will say angles subtended by the same chord BC. Okay, I will go with the first one, which is these two angles. Remember, the mission is to find 3 angles, just 3. It means there probably is more or just the 3. They're asking us to find and name those angles which are equal to D1. So we found the first one, that angle D1 is equal to angle A2, and these are angles subtended by the same arc. What arc are we referring to here? There's many arcs. There's arc CA, there's arc DA, arc DB, and arc BC. Which arc are you referring to? This is going to be our arc BC. Right. Now we're starting to look promising. Remember, now to find the next ones, we need to think of what they told us at first, which is that angle CAD is bisected by the line BA. And I told you that when you bisect it, it means angle A2 should be equal to angle A1. All right. Now, we already know that now D1 is also equal to A1, which was equal to A2. What was the reason there? It is given that angle BA, line BA bisects CAD, angle CAD. So when it bisects it, it cuts it into equal half. So we found 2 now. Now we're left with one more. Okay. To find the next one, this is a play field now. You ask yourself, okay, is there any other thing I can link to this angle? Effectively, if you fight here and try to find this one and see which other angles here are going to be equal to G1, I think we have fought a good run to find or to link D1 to one of the outside angles here. Now we need to use those angles to see which other angles are they equal to. Okay, we can focus maybe on A2. Let's look at A2 and ask ourselves, where is A2? Now A2 is between the line, is formed by the line BA and CA. Okay, that's the first thing. But A2 is also in a triangle. It is in a triangle FAC or ACF or whatever you want to call it. It can be AFC or ACF or FAC. This is the triangle that I'm referring to. All right. Now, is that just a normal triangle, or is there something special about that triangle? in this triangle, we can see that FA is a line that starts from the center to the circumference. That's the radius. And there's also another line, FC, which starts from the center to the circumference. That's a radius. So we can now certify this triangle as an isosceles triangle because those two are radius. Okay. Now, when we have a triangle that is named an isosceles triangle, what is special about it? An isosceles triangle has base angles which are equal. And what are the base angles there? A2 should be equal to C2. All right. So understand A2 is equal to C2, which is also equal to D1, right? Because we said D1 is equal to A2. What is the reason? These are angles, base angles of an isosceles triangle. What is the triangle? Triangle FAC. Right. We can go for another triangle, maybe focus on A1. We probably are going to find some fruitful results there, but they just need 3 for now. So forgive the question. Don't look for other angles. Now let's move on to the next question. The next question is asking us to show that the line DG is equal to the line GC. Okay. We're being asked here to show that the line, let me scrap this one. Show that the line DC, so this is 9.2, DG is equal to GC. If this line DG is equal to GC, what does it mean about this line that comes from the center to that line? That line goes in the middle of the line DC. It cuts into half, and they are effectively saying that prove that the line AB or the line FB or the line FG bisects that chord DC. Okay, does that ring a bell? Very first theorem, a line drawn from center perpendicular to a chord is going to bisect that chord. That's the very first theorem that we've learned. Okay. Now, here we're kind of stuck because that theorem says that that line must be perpendicular to that chord in order for it to bisect. But the question is asking us to prove that these two lines are equal, meaning they've been bisected. So the goal here must be changed to prove that indeed this line drawn from the center is perpendicular to that chord DC. Now, how can we go about that? We need to solve for this angle here. Okay, how do we go about it? Okay, so we've just proven that D1 is equal to angle A1 is equal to angle A2, and we also know that angle A2 is equal to angle C2. Okay, now we need to find the value of this angle here. One thing we need to note is that this angle A2 and angle G1 is in this triangle here. Triangle FDG is also in this triangle DGA. Okay. Another thing is that if you look here, these angles here are in the straight line DC. So if we were to find this one, we could probably even find this one. So you're basically asking yourself, where is that angle situated and what surrounds it? First thing I said is that it is in this triangle, it is in this big triangle, and it's also in a straight line. All right. Another thing we can say is that it is an angle here. There's an angle here, which is angle, let's say maybe G3. That opposite angle, so the opposite angles in a vertex are equal. So we have lots of rules that we can go about. Okay. Now, what do I choose? First thing one can go about is that if we decide to focus on this triangle here, focus on this triangle, then we need to find this angle and find this angle so that we can find that one. Okay, if we focus on this one, we will need to find this angle, we will need to find this angle. All right. And then we need to sum all those angles. Okay, so let's go for it. Another thing we can do is that we can also try and solve for the angle here, where we have already the angle 37. Okay, so which one can we go about? So the first thing you can note is that to find, let's say we're trying to look for this angle here. So if you look at this bigger triangle here, so let's look at that triangle. Triangle DAB. Because triangle DAB. So in that triangle there's A1, there's D, there's D1, there's D3, D2, and there's D1. Then there's just that angle B. Okay. Remember I said to you that if you go for this triangle, you need to find two angles. If you go for this one, you need to find this angle, one angle, which then you are going to use to solve, to prove that this one is 90. So if you look at this bigger triangle here, that's where we see that we can have a fighting chance because we have an angle here that is at the center, which I'm going to prove now. That if this is a diameter, look at angle, look at the line AB. If that is a diameter, it means this whole angle here, angle ADB, angle ADB is equal to 90 degrees because that is an angle subtended by a diameter. What is that diameter? Diameter AB. One can say the angle at center is 180, therefore the angle at circumference is 90. Another one is that, another reason you can say is that it's an angle in a semicircle. That is all equal to 90 degrees. Okay, now that we have that this angle here is 90, and we have this one, that we just solved it before, that we said it's equal to D1, which is 37. Can we find this angle? Yes, because all angles in a triangle should all add up to 180 degrees. So to find B, we can say angle B in this case, which is going to be angle ABD, plus this 90 degrees here, plus angle A1, which is 37 degrees. This should all add up to 180 degrees because these are angles of a triangle sum up to 180 degrees. You add all angles in a triangle, they should add up to 180 degrees. Okay, therefore we can calculate ABD by separating all of these from 180 degrees. Okay, so that is going to be 180 minus 90 minus 37. Okay, that is 53 degrees. This is 53 degrees. Okay, so we now have a new angle here, which is 53 degrees. 53 degrees. Okay, we've just adopted another kid. 53 degrees, we have 37. Can we find this last angle in that triangle? Yes, we can, because angles in a triangle should sum up to 180 degrees. So we'll repeat the same thing here. So we can say this angle B, G, D, plus angle 37 there, plus angle 53 degrees. So you can name them, these angles. This should all equal to 180 degrees. So these are angles of a triangle should add up to 180 degrees. I forgot to note that you need to tell us which triangle you are referring to. As you might see, there's lots of triangles here. So in here we're referring to triangle ADB. This was triangle ADB, and this one is triangle DBG. Alright. So we can solve here for this angle. Right. So angle BGD is equal to 180 degrees minus 37 minus 53. You can already tell here that 37 degrees plus 53 is equal to 90 degrees. Subtract that from 180, this is equal to 90 degrees. Okay, we're not done yet because we're supposed to prove that G1 indeed is perpendicular to, we need to prove that this line AB is perpendicular to DC and therefore bisects it. And we've just here said that indeed we are seeing that there's 90 degree here. So you can have 90 degree here, 90 degree here, 90 degree here. It still sees that this line is just perpendicular to this line. So by saying that, we can therefore now conclude to say that DG is equal to GC. Therefore, DG is equal to GC. The reason is that line from center perpendicular to chord will bisect that chord. Okay. Line from center perpendicular to chord will bisect that chord. But which line are we referring to? The line is line FG or line FB, or let's say, okay, yeah, line FG. Line FG drawn from center perpendicular to that chord. Which chord you're referring to is called DC, will bisect that chord. That's what the theorem says. Okay, now we've proven that indeed DG is equal to GC because it is bisected by that line from center. Okay, let's move on to the next question. Next question is saying that it is further given that the radius of the circle is 20 units. Calculate the length of BG. Okay, they're saying that the radius is 20 units. Calculate the length of BG. Where is BG? There is BG. Okay. But you're given that the length of this radius is equal to 20 units. Okay, now how do we work out the line BG? Okay, so let me say this. BG is in this triangle. BG is in this triangle here. Okay, but also BG forms part of a radius. So if you look, BG and this line here, we can tell that to add BG and GF, we are going to form a radius. So we can already tell that from here, if we can find the length of FG, so FG plus BG should give us the radius. Okay, so we can change the target to finding the length of FG. Because here in this triangle, we don't know the length of DB, we don't know the length of DG, we don't know the length of BG, which is what we're calculating. But if we were to shift to this triangle, we already know that there's a radius there, which is DF or FD. Do we know the length of this one? No, we don't. Do we know the length of this one? No, we don't. But what do we know internal to that triangle? We know that there's a 90 degree here, which makes this a right angled triangle. Okay, in a right angled triangle, let's draw that right angled triangle. We have angle D2 and also have angle F1. Okay, we know that this is effectively the hypotenuse of that triangle. Okay, but we don't have these angles. Can we find them? You can go with the easiest one. Can we find F1? or can we find D2? But we already know that, let's see, D3, okay. We can find this angle D2, because we said that while solving this triangle that the angle BDA should form a 90 degree. Do we have angle D1? Yes, we have it. Do we have angle D3? No, but do you see that D3, remember when we were asked to find angles that are equal to D1, we had to choose here whether we stick with A2 or A1, and we decided to go for A2. From A2, we could find that A2 is equal to C2, right? But if we had went for A1, we will say that the very same benefits A2 has, because this is a radius and a radius, this is also a radius and a radius, which makes it that angle D3 must also be equal to angle A1, which is equal to D1. Why am I saying this? Because this is a radius, which makes this an isosceles triangle. If that is an isosceles triangle, what do we know about it? The base angles of an isosceles triangle are equal. Okay, now since we have that, we can now put the reason to say that this is the base angles of an isosceles triangle. What is that triangle? It's triangle ADF. These base angles are equal. Alright. Now we have the angle D3. Can we find this angle that I'm interested on here? Okay. Angle D1 plus angle D2 plus angle D3 should all add up to 90 degrees. Because we've proven it here that this angle, all of it should form 90 degrees. Okay. Now we have D1, so we can have D2 being 90 minus the angle D3 minus the angle D1. We have the values of these ones because we said they are equal. So this is going to be 90 degrees minus 37 minus 37, which is going to give us, I think, 16 degrees. Okay, so we have 16 degrees there. And we are trying to look for, remember that we're saying FG plus BG. So FG plus BG is going to give us the radius. Can we find the length of FB? Yes. Think of it now. We have a right angle triangle. We have the value of the hypotenuse. We have an angle there. Can we link, using this angle, can we link this side to this one? What is this side? This is the side opposite the angle. And we have that there's also an hypotenuse. The what? Trigonometric ratio links those two sides. Cos is adjacent, the side adjacent from that angle divided by the hypotenuse. But sine is equal to the opposite over hypotenuse. So we can go for sine here. Where sine theta, in this case we have 16 degrees here. So sine theta, in this case our theta is 16 degrees, should be equal to opposite, which is FG, over hypotenuse, which is DF. Alright, we're trying to look for FG. So we can make FG the subject of the formula by multiplying by DF this side and DF this side. So DF, in other words, is just our radius. So DF sine 16 degrees. What is DF? DF is 20 units. Multiply this by sine 16 degrees. These are numbers, so you can punch all of this in the calculator. And make sure, very important, make sure that when you're doing this now and you're about to substitute here, make sure that your calculator is in degrees, because we are putting degrees here. Alright, so it's 20 multiplied by sine 16. That is going to be 5.51 units. .51 units. Alright. Now remember we said that FG added to BG should give you a radius, and we're looking for the length of BG here. So BG should be equal to the radius. The radius separated FG. This is going to be 20 units minus 5.51. This is going to be 14.49. Just check that. $14.49 units. All right. So that is the solution to our question 9.3. Okay. Do we have another question? Okay, that was our last question. So this marks the end of the video. As we usually say again, please give us the thumbs up. If you have any questions, which I hope you do, please leave them on the comment sections below. And don't forget to subscribe and refer the video to many more people. But before we continue, or before we end the video, we're going to give a chance to our audience to see if they have any questions that we might deal with. Okay, do you have any questions?
One question.
Yes.
I missed something. I heard you saying is it BA? That was bisecting angles. Which angles were bisected by BA?
All right. The question being asked on the audience is, I have mentioned that the line BA bisects some certain angles. And where are we getting that? That is the question on the ground. That am I just saying that, or we can prove that? Fortunately, this is mentioned on the statement. The statement reads as follows. In the diagram, there's AB, which is the diameter of the circle with center F. AB and CD, so it's AB and CD intersect at point G. FD and FC are drawn. Now there's a next statement here which says BA, line BA bisects angle CAD. BA bisects angle CAD. So this is a given statement, and we rightfully mentioned that on the start of the video, that what does it mean to bisect an angle. So this is where we have set the ground to say A2 is equal to A1, because the statement mentioned that this angle or this line bisects this angle. Okay, is that understandable?
Yeah.
Yes.
So can you use that argument? Because if you're saying that your BA bisects angle A, which means your A1 is equal to A2.
Yes.
So now, can you say, okay, because A1 is equal to A2, then the same line BA should also bisect F, which is F1 and F2. F1 and F2 should be equal because the angle at the center is called twice the angle at the circumference. Can you use that same logic?
Okay. The question is that if we're saying that the line BA bisects the angle CAD, which means A1 is equal to A2, can we effectively say that the angle F1 is also equal to angle F2? Because the angle at the center is twice the angle at the circumference. Okay, that is debatable. But, so if you go or you grow with the question, you'll see that we're meant to prove that DG is equal to GC, which means that if this line is drawn perfectly to divide these two lines to be equal, which will mean that if you're to draw a line from the center to the corner of that very same chord, that line is called the diameter, radius. So if you drew a radius like this, let me put it in green. If you drew a radius like this, and a radius like this one, that is gonna make your F1 to be this one and your F2 to be this one. Then it is unfair to say those two angles are equal, all right? But does it still not mean that an angle at the center is twice the angle at the circumference? So we'll then need to find a way to connect this to make the angle at the circumference. Yes, but now we're given a special thing to say that this radius are drawn such that it comes from this point to this one at the circumference and this point to this one at the circumference. These two are equal. We can, from that, make a foundation, or to say that we can prove, to say, okay, no, indeed, this line has to be bisecting this angle into half, right? It is not always fair to say, okay, if we have a, let me draw it. For instance, okay, let me say, it is not fair to say that if we were to draw a line from the circumference bisecting the angle at the center, because that is an angle at the circumference, and it is half the angle at the center. So this is A, B, C. So A, B, C. Am I right to say that A, B is twice the angle AC? I drew this bad. This should be, let's say it connects there. Do we see that? Is it fair to say that the angle AOB is twice the angle ACB? Is that fair? Because the angle AOB, this angle AOB at the center, is twice this one.
Yes.
All right. Now if I say, if you were to draw a line from the circumference that bisects that angle, so into half, angle 2, and then so this line and this one, does it mean that that line also cuts the one at the no, it doesn't. So I want to say that in this specific statement, we are fortunate to say that indeed F1, we can prove F1 to be equal to F2, but that is not always the case, that if we were to bisect an angle at the center, at the circumference, those two angles will subsequently make the angles at the center to be cut into half also. So in a sense, you are right to say F1 is indeed equal to F2, but you can prove that.
So okay, so you're saying in general it's not always true.
Not always true.
As you have demonstrated there.
Yes.
So in this case you can say your F1 will be equal to F2 because let's say you're given that A1 will be equal to A2 from the fact that they are bisected by BA. So now you can say, okay, now my A2 is subtended by BC, right? And my F2 is subtended by the same BC. Do you see that?
F2?
A2 and F2 are A2 and F2 are subtended. So we see that relationship. So if these two are equal, A1 and A2, then these two should also be equal. So
wait, which two? F1 and F2.
Yes.
We are trying to prove it now that
Yeah,
they are
that
equal.
they're equal.
Oh yeah, so
So like I said, you can say
you are right. You are right.
you're saying A1 is called A2, but now A2 is subtended by BC.
Yes.
So yes, so F2 is equal to twice A2.
All right.
And then this is equal to this.
This is
A2 is equal to, A1 is equal to, not equal to A2, but A1, F1 is equal to twice A1. So therefore, those should be the same.
Okay. So this thing, okay, let me say, depending on which point, so the question on the floor is that if we're trying to prove that indeed F1 is equal to F2, so we have another question here. Let me try and wrap here so we can conclude this one. I'll take off this one. We have question number 9.4 from the audience. But I would like to make this question not 9.4, I would like to make it to be 9.1, which is before anything else. Or let's say 9.2, when we have at least found which other angles are linked to D1. So we can say this was question number 9.3. The one that we solved now was 9.4. Now the one we're looking for is 9.2. Why am I saying these things? Is that when we are taking this question 9.2, we don't know yet that DG is equal to GC, right? And they are asking us to prove that F1 is equal to angle F2. Now in the audience, they're saying that there's an arc here which subtends F2 and also subtends the angle A2. So the arc here that subtends this angle at the center, that angle at the center must be twice that angle at the circumference. Okay, so we're saying F2 should be equal to 2 times the angle A2, and this is because angle at center is 2 times angle at circumference. Okay. The other thing is that the audience is saying F1 should be equal to twice the angle A1. And my question is, why are we saying that? Why would we say that?
Sorry?
Why would you say angle F1 is equal to is twice angle A1?
Because they're both subtended by dB. So they're both subtended by the same arc.
Yes.
Chord.
Yes. So that is correct. F1 is equal to 2 times angle A1 because these are same thing, but this one is subtended by the same arc dB and this one is subtended by the same arc BC. Alright, but how do we conclude that this angle F1 is equal to angle F2?
We say we're told that BA bisects angle A. So A1 is equal to A2. We're told that our BA is bisecting this angle, bisect this angle down there, which is our A1 is equal to A2.
Yes.
Therefore, F2? F2 is equal to A1,
Yes.
which is the same as F1.
Yes. So, rightfully so. Now, we are using the fact that, so that's why I'm saying strategically that if we place this question at 9.2, then we at least can use the fact that we have already these angles, which is angle 37. But the main what is the aim of this question is not to prove that what is the value of this angle, is to prove that this indeed is equal. Now we can safely say that if this angle is twice this one and this one is twice this one, and we have already proven that these angles are the same, therefore this one being twice this one is the same as this one being just twice this one, right? Which makes it that these two are equal. That is correct. Another approach would be that having these two angles, which is, let's say, angle X, right? We have just mentioned that this angle here is, let me see. So we can say that this angle is half this one, so which makes this one to be 2x. All right. Now our goal will be to prove that indeed that this is angle X and this one is also angle X. How do we do that? If we look at this, so if this is, oh, no, let me do it this way. If this is angle X, this is angle X, then this angle is equal to 4x, the whole of this angle. So we need to prove that this one is equal to 2x, right? And I've told you here on the previous question, if you look at that triangle, it looks like this. There's angle A, there's angle C, and then there's a nice line here which makes angle O2 or F2. We have mentioned that these two are equal because this is equal, right? So if we have x here, this must also be equal to x. We know that the exterior angle of a triangle is equal to the summation of these two, which means that this is effectively 2x. But if they have to make 4x, we can clearly say that this is 2x. So that is another way to go about it. So it's just a matter of playing around whatever method you can go about.
Yeah.
Okay?
So the reason I asked this question,
Yes.
the way you looked at 9.2 of proving, I'm not sure what you're proving those equal lengths.
Yes.
I thought of it maybe I would need to prove that those two angles are equal, which is F1 and F2. Once I have that, I can simply use congruence of triangles because I have two congruent triangles from there. But the look of think of a diameter, then sometimes 90 degrees, and it was stretching.
Yeah, so what we're effectively getting from this question is that there are many ways of killing, I think it's a cat or a mouse or whatever, but there are many ways of killing this thing. So one can go for congruence, which is that if we're to prove that these angles are the same, and this angle is the same as this one, then effectively we do have this one. Because these angles should be equal to this. So we can effectively say that these are being split into two equal angles also.
Or we can just say, we're using congruence, which means in that case, you see you can say in both triangles, the left one is GDF and GCF. You can say in that case, you know that GF is equal to GF because that is a common line.
Yes.
And then you can say angle F1 is equal to F2 because you've proved that they are equal.
Yes.
And then you say your
Therefore,
FG and your FC, they are radii of this triangle. Therefore, these two triangles are equal, are congruent, which is they are identical by side, angle, side.
Wonderful.
Therefore, you can just say if they are identical, this DG and
equal.
GC, they are equal because they are corresponding sides of congruent.
Perfect. You can go for congruent
Like-
triangles or similar triangles. Similar triangles, what you have from there is that this angle is equal to this one is equal to this one. Therefore, we can say that these angles are similar or proportional, which means that if we were to divide corresponding sides here, if we divide this side by this one, that's a ratio of 1. Divide FG by FG, that's a ratio of 1. That effectively makes this one also be equal to this one because we must attain the same proportionality throughout. Similarity to congruence, there are many ways of killing the baboon. Okay, thank you guys. That is our last question. Please bring these questions and hopefully you found today's sessions to be conducive. All right, thank you.